Hey everyone, so this is going to be a video for section 5.2. Make sure that you have read section 5.1 before watching this, or else some of these things may not make as much sense. This is predicated on having read 5.1 because 5.1 introduces the idea of probability distributions. So the focus of this section or rather, the focus of the last section was on discrete probability distributions, or PDFs. To find the PDF for a situation, you usually needed to actually conduct the experiment and collect data. Then you can calculate the experimental probabilities. Normally, you can't calculate theoretical probabilities instead. However, there are certain types of experiment that allow you to calculate theoretical probabilities. One of these is called a binomial experiment, or a Bernoulli trial. The Bernoulli family historically was very interesting. Entire family of prestigious mathematicians. So we have here some properties of a binomial experiment. There are a fixed number of trials n, which means that the experiment is repeated a specific number of times. The n trials are independent, which means that what happens on one trial does not influence the outcomes of the other trials. There are only two outcomes, which are called a success and a failure. And the probability of a success doesn't change from trial to trial, where P is equal to the probability of success and Q is equal to the probability of failure. If you know that you have a binomial experiment, then you can calculate binomial probabilities. This is important because binomial probabilities come up often in real life. An example would be tossing a fair coin 10 times and finding the probability of getting 2 heads. Or shooting 5 arrows at a target and finding the probability of hitting the target 5 times. Let's look at an example. Suppose that you are given a 3-question multiple choice test. Each question has 4 responses, and only one of those responses is correct. Suppose that you want to find the probability that you can just guess at the answers and get 2 questions right. It says here, teachers do this all the time when they make up a multiple choice test to see if students can still pass without studying. In most cases, the student can't. And in fact, certain tests like the SAT are balanced out so that you, if you end up guessing for all of your answers, typically you net 0 points on average. To help with the idea that you're going to guess, like you genuinely can't figure out the questions, let's suppose that the test is written in some Martian language. What is the random variable? Here, our random variable, x, let me move this down, is going to be the number of correct answers. Is this a binomial experiment? Let's go get our criteria for something being a binomial experiment. Binomial experiments have a fixed number of trials. That's true for this case. Here, n equals 3. There are 3 questions. Number 2, The trials are independent, which means that what happens on one trial does not influence the outcomes of other trials. Well, getting the first question correct, for instance, has no effect on getting the second or third questions correct. So the trials are independent, right? Getting one question right has no effect on getting the others right. I think it should be this one, right? Let's see. For this third one, there are only two outcomes, a success and a failure. That's true. You either get the question right or you get the question wrong. And for this this fourth criteria, the probability of success doesn't change from trial to trial. That's correct. The probability of getting a question right is always 1 out of 4. We said that there were 4 possible answers. So the probability of getting a question right is 1/4. 1 out of 4. So the probability of success here is P, which is 1 out of 4. And Q is 1 minus this, which is 3 out of 4. So we have all of these properties that are met. So this is a binomial experiment. And for C, what is the probability of getting 2 questions right? So let's see. This is asking for the probability of getting exactly 2 questions right? Well, let's start by looking at the sample space here. My sample space or all of my possible outcomes here. Let's say that R is right and W is wrong. Then my sample space is going to be R, 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 W, R, W, R, W, R, R. Let's see. W, R, W, R, W, W, and W, W, W. Let's see. 1, 2, 3, 4, 5, 6, 7. Let's see. Did I miss one? I missed WWR. So WRR, WWR, there we go, WRW, RWW, and WWW. W, where each of these letters indicates whether we got that question right or wrong. So RRR is we got all 3 of the questions right. RRW is we got the first 2 right and the last one wrong. RWR means we got the first question right, the second question wrong, and the third question right, and so on. Now, previously what we did was we would have looked at all of the possible ways to get 2 questions right. Which would be this, this, and this. And we would have divided this by, and to be clear, that's our event space, right? Our event space here is RRW, RWR, WRR. We previously would have taken the number of things in our event space and divided it by the number of things in our sample space. But this does not give us the correct answer in this case because the probability of getting an answer right is different from the probability of getting an answer wrong in this case. So let's look at the probability for just one of these, for instance. What's the probability of RRW? Well, this is going to be P times P times Q. We said that P was our probability of success and Q is our probability of failure. And this is 1/4 times 1/4 times 3/4. And this is going to be the same for these other 2 as well, right? So the probability, I keep writing an R for I keep going to write the RWR a bit too soon here. For instance, this probability, this is going to be P times Q times P, which is 1/4 times 3/4 times 1/4. This is the same thing as the previous one because multiplication is commutative. And it's going to be the same probability for WRR. This is going to be Q times P, which is 3/4 times 1/4 times 1/4. And let's see, what is this? This is 3/64, right? So the probability of getting 2 answers right is what I get whenever I add up all 3 of these probabilities. It's PRRW plus PRWR plus P of WRR, which in this case gives us 9/64. And for D here, what is the probability of getting 0 right, 1 right, or 3 right? The probability of getting 0 right, this would be, let's see, that would just be this WWW, right? This would be just Q times Q times Q. This would be 3/4 cubed. And really, this is the same thing as, let's just write this as 1/4 to the 0. This is p to the 0th times 3/4 cubed. And this works because anything to the 0th power is 1. So this is the same thing as multiplying 3/4 cubed times 1. The reason why we're writing it like this is going to be important momentarily. And let's go ahead and look at that reason. Let's look at this thing called the binomial formula. This might look a little bit scary at first, but it's not bad. The binomial formula for the probability of R successes in N trials is given here. The probability that X is equal to R, so the probability of R successes in these N trials is, and it's given here. This is N choose R times P to the R times Q to the N minus R. So this, I need to choose a different color here. This is the number of combinations of N things taking R at a time. It's read N choose R. This is also a common notation for it. N with this exclamation point that you see here, where we define N choose R. This means that you are finding, this is called a factorial. This is called a factorial. This means that you're multiplying a number times that number minus 1 times that number minus 2 all the way down to 1. And the example that they give here is that 5 factorial is 5 times 4 times 3 times 2 times 1. So you're just taking a number and you're multiplying it by every number below it all the way down to 1. And we're going to use this formula to very easily calculate some probabilities. When looking at a person's eye color, it turns out that 1% of the people in the world have green eyes. Consider a group of 20 people. The first thing we're going to do here is state the random variable. The random variable here is going to be the number of people who have green eyes. For arguing that this is a binomial experiment, there are 20 people, and each person here is a trial. So there are a fixed number of trials. If you assume that each person in the group is chosen at random, then the eye color of one person doesn't affect the eye color of another person, right? It wouldn't make sense if it did. So the trials are independent. A person either has green eyes or they don't have green eyes, so there are only two outcomes. And the probability of a person having green eyes is 0.01. Right? As a probability, this we would write this as 0.01 as a decimal, right? This is the same for every trial, since every person has the same chance of having green eyes. So here, P is 0.01, and Q is going to be 1 minus this, which is 0.99. So for C, we want to find the probability that none of these people have green eyes. let's look at our formula. So this is n choose r. So I guess, well, first of all, we should write this as we're looking at the probability that x is equal to 0 here. This is, let's see, n choose r. N here is the number of trials, which is 20. I'm going to write this in this alternative notation like this. So this is 20. And here I want to choose 0 times let me move this down. Let's see, p to the r power. So this is going to be 0.01 to the r power, and r is 0, times q to the n minus r power. So this is 20 minus 0, which we know is just going to be 20. We can quickly work out what 20 choose 0 is going to be. You might actually have an idea of how many ways there are to choose 0 things, but let's write it out. 20 choose 0. This is 20 factorial minus 0 factorial times 20 minus 0 factorial. And just for reference, we define 0 factorial as being 1. We define 0 factorial, this 0 with the exclamation point, we define as being 1. So this ends up just being 20 factorial over 1 times 20 factorial. So 20 choose 0 is 1. There's only one way to choose 0 things from 20 things, right? There's only one way to choose nothing. And the rest of this is just a matter of plugging stuff into a calculator. So now that we know that p of x equals 0 is 1 times all of this. Oh, and remember 0.01 to the 0th is also actually 1, because anything to the 0th power is 1. Then this simplifies down to 0.99 to the 20th power, which in a calculator gives us 0.818. And let's find the probability that 9 have green eyes. So once again, we're going to use this formula. Here we want the probability that x equals 9. This is going to be 20 choose 9 times p, which is 0.01, to the 9th power times q, 0.99, to the 20 minus 9th power. So 20 choose 9. This is going to be 20 factorial divided by 9 factorial times 20 minus 9 factorial times 0.01 to the 9th times 0.99 to the 11th. Let's see, this is 20 factorial over 9 factorial times 11 factorial, because 20 minus 9 is 11, times 0.01 to the 9th times 0.99 to the 11th. Now, because 20 factorial is 20 times 19 times 18 and so on, remember 11 factorial will be 11 times 10 times 9 all the way down to 1. I can simplify this expression on the left a little bit. This is really, let me think if it's really worth writing out. You could write this as 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12 over 9 factorial. But I think that that's a little bit too much to write. So at this point, we would really want to use a calculator. There are calculator buttons typically for these factorials. You typically don't have to type out all of this. There should be buttons on your calculator. On a TID3, TID4, I'm not exactly sure where they are. Online calculators also work just fine. But if we plug all of this into a calculator, we should get 1.5 times 10 to the negative 13th, which is about 0.000. This is a very, very tiny value. There are going to be a lot of leading zeros here. And for these last two, oh, I didn't mean to undo there. For these last two, I'm going to leave these as examples for the reader and watcher. All right, so that will be it for 5.2.